Okay, so looking at this, that kind of gives you an idea what to expect about crystal types on the next test. Now, what do we want to talk about next starts to combine several concepts about energy changes during changes of state, going from solid to liquid to gas. We've talked about energy in the last chapter where we looked at how much energy does it take to warm something up, specific heat times mass times delta T. And then we introduced energies or enthalpies for phase changes, the enthalpy of vaporization that we looked at in the Clausius-Clapeyron equation. We can also look at the enthalpy of fusion, and we can start to think about the energy changes as we move from one physical state to another. When we think about physical states, the intermolecular distances are different in gases, liquids, and solids. As you can see, we talked about this before in terms of molecules touching, but the molecules are really far apart in a gas. They're closer to each other in the liquid, and they're really close in the solid. So it takes energy to move these molecules apart and then to allow them to make a phase transition. And we can look at and calculate the energy that it takes to do this by looking at heating and cooling curves. So as we look at a heating curve, we're going to be looking at the temperature increasing on the y-axis, and we're looking at the heat energy added on the x-axis. So when we look at this, we start off at down here, we're at some temperature, and we have our material, and it is a solid. As we add heat, the solid warms up. So here, I am heating my solid. Now, all of a sudden, I've got my solid warmed up. I'm still adding heat, but all of a sudden, this flattens out. Even though I'm adding heat, the temperature is not changing. That's because I'm using the heat added to make a phase change. The heat that's adding is actually melting my solid. So we're melting the solid. So in this flat area of the curve, I have some solid and I have some liquid. Then all of a sudden we get to the point where all of my solid is melted, and now the temperature starts to go up again. I'm adding heat and the temperature goes up. So now I am heating my liquid. After I heat the liquid for a while, I get another spot where I'm still adding heat, but all of a sudden this flattens out. Now you'll notice that this flat area is much longer than this flat area. Make sure you draw that way so that this is flatter. And this is where I am having evaporation. I am making the transition from the liquid to the vapor, so I have liquid and vapor in this area. Then again, I get to this point, and all of a sudden, the temperature starts to go up because I am actually heating the vapor. You ever hear anybody say, oh, steam burns worse than water, boiling water? It does, because you get into this area when you've got the spaghetti pot boiling, and it's in that closed area, and you're adding heat with the fire going under your pot, then you're heating that vapor in the closed space, so it's getting to a much higher temperature. And when you take the lid off the spaghetti pot and point it towards yourself instead of pointing it away, that vapor can encompass you, and it can cause really severe burns. Okay, and you get more heat transfer because of that. You ever know why they spray oranges with water during the night when it's cold in Florida? It does keep them warm. It prevents them from freezing, because what happens is when they get a cold snap in Florida, it's usually only a few hours. So they go out in the orchards and they start hosing the fruit down. They get it dripping wet. And what happens is, as the heat is removed from that water to make the water freeze, it takes time to do that, and so it actually protects the fruit inside. The water on the outside is freezing and the fruit doesn't freeze, and then usually by the time they get all that hosing down done, the sun comes out, melts the ice, and it saves the fruit because it's removing, because of the latent heat, it's actually freezing the water and not the fruit, so it's kind of a good deal. So when we look at this, we can think of this curve having 5 different areas. In the first area, we heat the solid. The second area, we melt the solid. Then we heat the liquid, evaporate the liquid, and heat the vapor. And we're going to do some calculations where we can determine how much energy it takes to go from any one point on this curve to another. And we learned in Hess's law that if you do something in steps, it's the same amount of energy if you add them together. So we could figure out how much energy it would take to heat this solid, melt it, heat the liquid, evaporate it, and heat the vapor, and then we can add them all together. And that's the kind of problems we're going to look at. So you see that when we get to the flat places, we're making a phase change, and you see that this one is longer because the intermolecular distance difference is bigger going from liquid to gas than it is going from solid to liquid. So now we also can look at how much energy it takes depending on the intermolecular forces. If you have hydrogen bonding, you're going to have higher enthalpies of formation because you're breaking those bonds apart. So now let's look at the cooling curve before we do any math. The cooling curve, now we're looking at temperature again on the y-axis, but now instead of heat added, I'm looking at heat removed. So I start off hot and I'm cooling this down. So we start off here with a hot vapor and we cool it down. Then all of a sudden this curve flattens out again, just like we'd expect. So here I am cooling the vapor. What's going on in the flat? Phase change. I'm condensing the vapor. So I have vapor and liquid in this flat spot. Now what happens? Now I cool it down some more, right? And now we are now cooling our liquid. Now, what would you expect would happen next? Flatten out again, right? You'd expect that it would just flatten out here, but it doesn't. What happens here, it makes a little dip, and then it flattens out. So here, we are freezing the liquid, and then all of a sudden, we are cooling the solid. So let's talk about that little dip. We don't get a sharp transition when we make the phase change or when we initiate the phase change from the liquid to the solid. And the reason for that is when you go from a gas to a liquid, you just have the molecules bumping around, they crash into each other, lose energy, and they fall in the liquid, and the liquid molecules are moving all around. But in the solid, the molecules have well-defined little places where they have to be in their crystal lattice. So it takes time for them to get in there. So what's happening is we're cooling the liquid down. We get here, and all of a sudden the molecules say, oh, hey, it's cold in here. We should get in the lattice. But the temperature keeps going down because it takes them time to get into their positions. The best everyday example I can give you is what I used to see when my kids lived at home and rode the bus to school. The bus stopped at my house. We owned the empty lot next door, and it would stop right in front of the empty lot. So I would send the kids outside to get on the bus, and I would stand in the living room and look out the window so I could see them, but I didn't have to go stand out there where it was raining or cold, make sure they got on the bus and didn't play hooky or get abducted or whatever. So I would stand in the living room watching the kids in the bus stop, and they had about, 15 or 20 kids from our neighborhood all got on the bus there. So they would come, and they would just kind of hang out in the empty lot waiting for the bus to come. And apparently there's some kind of a pecking order involved in riding a bus, and where you sit and who you sit with has social implications. I didn't know any of this culture because I never rode a bus to school. It's true, right? You guys? It's segregation on the bus? What, where you send the little kids to the back of the bus or something? I don't know. Anyway. Oh, so the big kids can be naughty in the back, yeah. So apparently there's some culture on the bus, and where you sit is important. So what I would observe is the kids would try to get to the bus stop early so that they could get a good seat on the bus. It just so happened that our bus stop was the first one. An empty bus stopped in front of my house. The kids all got on there. That was the first load of kids they picked up. So what I would see is all the kids would get there. As soon as they got there, they took their backpack and they dropped it at the curb. And apparently they had decided which way the line went. And then kids would come and they would line up their backpacks, and that would hold their place in line for when the bus got there. Then they would go running around, chasing each other. There were twin brothers that lived next door, and they'd pound on each other. One day I had to go out and fix a bloody nose before the bus came. And there'd be all kinds of social interaction going on. Then the bus would come around the corner a block away. One of the kids would yell, "Hey, there's the bus." And they would all rush to the front by the curb where their backpacks were lined up. And as these 20 kids came rushing, they kind of formed a big blob. And they would take a time while they were all jockeying for positions, and this blob of kids would turn into a whole bunch of kids lined up right next to their backpacks. And they would get into line, and they would then dip down, grab their backpacks. Just as the bus pulled up, the door magically opened, and they would march up onto the bus with their backpacks like little soldiers in a very nice straight line. And then they would drive away, and I didn't have to deal with them for 8 hours, right? So that's what's going on here. It takes time for the kids to see the bus, jockey for position, and then grab their backpacks. And when they get ready to get into the crystal lattice, then you actually warm up to the freezing point. And this is called supercooling, where the liquid goes below its freezing point and then warms up. So we can actually do some calculations with this, and that's what we're going to do next.